And welcome to Resonance in RLC Circuits. This is an ECE 4823 project for Georgia Institute of Technology. First of all, what is resonance? Resonance is the tendency of a system to oscillate at greater amplitudes at some frequencies than at others. To help show the idea of resonance, I'm going to look at a mechanical example and an electrical example. The mechanical example I'm going to look at is a simple pendulum. The differential equation that can be used to describe the motion of a pendulum is the first equation shown, and that can be simplified down, and once it's simplified you can use the central difference approximation to approximate theta, which is the angle, at future times. So what you're seeing here is a simulation of the pendulum. So you can see it in blue and it's just swinging, and it's not going to stop swinging because there's no damping. So what I did to simulate this was I used the future times for theta to find the distance the pendulum travels from its equilibrium position. I then plotted its position versus time, which you can see on the graph. So this graph just helps show the idea of resonance. What's going on here is that the signal in blue is the natural frequency of the circuit, and the signal in red is the output. So there's an input force that's going 0.75 times the natural frequency. So every third cycle, the two signals are in phase with each other, and they add together to give an amplitude which is bigger than the original input into the system, and this is resonance. So next up, I wanted to look at an electrical example, and electrical resonance is kind of similar to mechanical resonance in that if the input signal is going the same frequency as the natural frequency of the circuit, well then the output voltage can actually be larger than the input voltage into the circuit. So I just chose to look at a simple LC circuit, so there's no resistance, so there's no damping, and there's also no input frequency. So as you can see, resonance is occurring because the output, which is in red, has a higher amplitude than the natural input frequency into the circuit, which is in blue. So now I wanted to look at an RLC circuit, which is a lot more interesting because there's going to be input into the circuit and there's also going to be a resistance which may cause damping. So we're going to look at the output voltage, which is the voltage across the capacitor, which is shown. And the way I calculated the instantaneous voltage across the capacitor is the equation shown here, and that can be derived from Kirchhoff's voltage law. I then use the central difference and the backwards difference to help approximate the voltage at different times over the capacitor, except this created a second order error in my simulations. So I looked at it in relation to three different inputs: a DC input, an AC input, and a step function. So first of all, I looked at a DC input, and if a DC input has no initial values, well then no resonances can occur. This is because there has to be a changing voltage across the capacitance for resonance to occur. So in my first case, I just showed this, and I have the initial voltage at 0 and the initial current at 0 and a resistance. And as you can see, nothing happens in the circuit, and there's no voltage across the capacitor or the inductor. So then I set my initial voltage to 1 volt. And as you'll see, the capacitor starts to discharge. This is because there's no changing voltage, so the voltage across the capacitor can't increase, but it starts to discharge due to the resistor in the circuit. But because the resistor is so high, it means that no resonance can occur, which I'll explain more later. So next I looked at an AC input, and AC inputs can easily cause resonance if the input to the circuit is the same as the natural frequency. So I used a bode plot to help illustrate this idea of resonance. What you're seeing is the magnitude on the y-axis and the different frequencies on the x-axis. And you can see that with different input frequencies, the magnitude starts to increase, and then at one certain point the magnitude is at its max, and this is the resonant frequency. So now I'm going to show you a simulation of this Bode plot, where first of all the input frequency is going to be the same frequency that the max magnitude occurred in the Bode plot. So you can see that the capacitance value initially starts to increase until it starts increasing way past the input value. And at this point it's reached its resonance. And because the input frequency was the resonant frequency, this is going to be the max amplitude that the circuit is ever going to reach. So now I looked at a frequency which is slightly below the natural frequency. So the input frequency is actually 0.75 times natural frequency. So you can see from the simulation that the amplitude doesn't come close to the amplitude reached in the last case. And that's because sometimes the input frequency is combining with the natural frequency of the circuit, but it's actually causing a decrease instead of an increase, which occurs in resonance. So you can see that sometimes the amplitude actually decreases. So damping has a major effect on resonance, and I chose to look at damping mostly with step functions. So damping can either be underdamped, overdamped, or critically damped. So I'm going to look at overdamping first, and I'm going to look at a mechanical system and an electrical system. So I decided to go back to my mechanical examples to help show this idea of damping. And in the first case, the pendulum bob is overdamped, and it's overdamped by an awful lot. So this means that it reaches its equilibrium point, which is the very middle, but it does this very slowly with a lot of resistance. So using a step function as an input, I wanted to show this idea of overdamping in an electrical system. So as you can see, the output voltage reaches the input voltage, which is the top voltage in blue, but it does so very slowly, and it also decreases very slowly, but you'll also notice that there's no resonance in the circuit. So now I want to look at critical damping, which is when zeta is equal to 1. So you can see in the mechanical example that it reaches the equilibrium point as quickly as possible, but the bob still isn't resonating. So this is my electrical example, and you can see in the electrical example that the output voltage goes up to meet the 1 volt input voltage, and it does so a lot faster than in the previous case. And also you can see that the shape of the output voltage matches the shape of the input voltage a lot better, but also there is no resonance in this case. So now we're going to look at underdamping, where zeta is less than 1 and there should be resonance. So you can see in the mechanical case that the pendulum bob again reaches the equilibrium point very fast, but this time it starts to resonate instead of staying straight at the equilibrium point. This is because the damping is so low and that the resistance is low, so that it can actually resonate. So in the electrical example, you can again see that there is resonance. It goes up and it meets the 1 volt point, and it does this very fast, and then it resonates at 1 volt for a few seconds. And this is because the resistance is lower in this case, which allows the voltage to lose less energy and to resonate. So my last simulation is another underdamped example, but in this case underdamping is really, really low. So what we expect to see is an awful lot of resonance, as hardly any energy is taken out of the circuit from the resistor. So again, the pendulum bob it starts to resonate, and it doesn't meet the equilibrium point in this case for a long time. This is because there's hardly any resistance, so that means that the pendulum bob can continue to swing and only lose a small amount of energy during each cycle. So the electrical example is pretty similar to the mechanical example in that it resonates way past the input voltage of 1 volt, and then it continued to resonate for much longer than it did in the previous case. And then this happens again when the step function goes back down to 0. So the resonance is the highest when the damping is low. So that's my video. I hope you enjoyed watching it and you learned something about resonance.